So now we shall look at the Dijkstra's algorithm. The Dijkstra's algorithm is a very simple algorithm to find shortest path. So the goal is to find shortest path from any given vertex to all other vertices. So here's a graph, and let's take an example. We want to find the distances, that is the shortest path distances from B to all other vertices in this graph. So we do the initialization first. And since I am going to start with B, I have colored B in this table here red. So I have this table and this row corresponding to B is red. I have three columns in this table. The first column is a list of all the vertices in the graph. And the second column is the shortest path to that vertex from B. And since I'm initializing, I don't know the shortest path yet, so I put infinity as the entries everywhere except in B, because it doesn't make any sense to put infinity in B because I'm beginning from B. B is the point where I begin my iterations, and the distance of B to itself is obviously 0. And then I have a third column here, previous vertex. So when I'm going from B to any other vertex, I have to have a path which is a sequence of vertices. So in that path, what's my previous vertex before I reach my destination? That is going to be filling up this column here. So now I begin my step 1. In step 1, I will be rerouting everything through this B. So B I have marked orange. I'll call everything, all vertices that have been marked orange as visited vertices. So B is a visited vertex at this point. And since this is step 1, all I do is I'll be looking at the routes which are direct edges from vertex B. So that's why I've marked this 1.5, 4.0 and 1.5 red, because I'm looking at anything that comes out of B. So from B to A is 1.5, so I fill out this 1.5 here, and the previous vertex is B, because in order to reach A, so far the shortest distance is 1.5 and I have to enter B via A. Likewise, from B to D, the distance found so far is 1.5. So to D, I look at D here, column D, and the distance is 1.5. Finally, the distance to F here is 4.0, and that's through this edge here, which has a weight of 4.0. Step 2. Now I'll try to reroute everything through this vertex A. In each step, I will be trying to reroute all existing paths through a new vertex. So I'll sequence through the remaining vertices. Step 2 is A, B is done already, so then A, then C, then D, E, F, and G. Each step a new vertex. I'll try to reroute all my existing routes through this new vertex. This time, in step 2, I'm looking at A. And since I'm looking at A, from A, I can only reach F and C. Therefore, I've colored these edges, A to F and A to C, red. I didn't bother about coloring this 1.5 that's connecting A and B red because B has already been visited. It's a visited vertex, so I don't worry about it. Now, in order to reroute any path through A, I will obviously have to enter B, and the shortest path to B is 1.5. So I will have to use this 1.5 to get to A. So I've colored this 1.5 red also. So now let's see. From A, I can go to C. What's the distance to C that I found so far? Infinity. If I, so the distance from B to C that I found so far is infinity, and that's why this is the straight distance which I have marked in green. Now, what if I reroute through A? What do I get? So B to A is this 1.5 here, and then A to C is this 1.0 here. 1.5 and 1.0 is smaller than the infinite that I had found so far, and therefore I replace the infinite with 2.5, which is 1.5 and 1.0. And the previous vertex, I update it to A, which means that in order to enter C, so far the best path that I found is through A, this A, and the distance, the shortest distance is 2.5. Now let's look at what happens to F, because from A I can only go to C and F. So far the distance to F is 4.0 here. Now if I reroute through A, what do I get? B to A is 1.5, which is in red, and A to F is 1.8, which is this red here, and 1.5 plus 1.5 plus 1.8 is 3.3, which is less than 4.0 here, and so I will replace the existing path, existing distance from 4.0 to 3.3. And in order to get to 3.3, so since I rerouted through A, I update my previous vertex. So now the shortest path to F found so far has a distance of 3.3, and in order to enter vertex F, I have to go via A. So this is my table at the end of step 2, and I have at this point marked B and A, these vertices, as visited. Now let's go to step 3. In step 3, I'll try to reroute all the existing paths via vertex C, and therefore I have marked this weight 0.7 red, because from C the only vertex I can jump to is F. I can also go to A, but A is a visited node, a visited vertex, so I don't care. So from C, let's see if I can do any improvements to my existing path. So from from B so far to F, the shortest path that I've found has a distance of 3.3. Now, if I reroute that path through C, I'll be using up this 2.5 here and this 0.7 here. In order to reach C, I'll use up this much distance, 2.5, and then from C, if I go to F, I will use 0.7. 2.5 plus 0.7 is 3.2, which is less than 3.3, which is what I had found so far. Therefore, I'll update it. So now what I have is from B to C was 2.5 and from C to F was 0.7. They added up to 3.2, and so my new shortest path has a distance of 3.2, and that's through C. End of step 3. Now step 4. In step 4, 1.1 and 1.2, these are the only edges that go to E and G, and I don't worry about this 1.5 here. I don't color it red because it's connecting me to a marked visited vertex. So now here, in order to go to any other vertex through through D, I have to use up this 1.5 here. Now, what do I have? From D to E is 1.1. So far, I found a distance of infinity, but if I reroute my existing distance of infinity through D, then it's 1.5 plus 1.1. That's 1.5 plus 1.1 is 2.6. That's smaller than infinity, so I'll have to replace this with 2.6. Likewise, I have to replace this infinity to G here with 1.5 plus 1.2, that's 2.7. So I update those two rows, and now the previous vertices were D. I move on to step 5, and I mark vertex E as visited, and the distance so far to vertex E is 2.6, which has been colored red, and the only place I can go to through E is vertex G. And the distance to vertex D found so far is 2.7. Is 2.6 plus 1.6 more or less than 2.7? It's actually more than 2.7, so that doesn't do me any good. So in step E, I don't have to update anything else. Step 6, now I'll be looking at everything via vertex F. And I found the distance to vertex F to be 3.2 so far, and it doesn't do me any good. I already have a shorter distance to G, and G is the only other vertex that I can reach from F, which is not visited yet. So no changes here. Step 7, likewise, there's no further change in the table. So at the end of Dijkstra's algorithm, this is what I have. This is the final table. And I can find out the path from B to any other vertex using this table. So here's F as an example. So I want to find what's the path from B to F. From B to F, I already know that the distance is 3.2, but what's the complete path? All I have to do is, I'll read off, okay, in order to go to, F, I have to enter F through C. So this is the edge. And then, see, I go to C here. How do I enter C? Via A. Through this edge, which I now colored red. And likewise, how do I enter C? How do I enter A? It's directly from B, and so I mark that edge red. And so this gives me the shortest path from vertex B to vertex F. So now let's look at the algorithmic complexity of Dijkstra's algorithm. Now the number of edges is approximately between the number of vertices for a sparse graph. It's proportional to the number of vertices for a sparse graph up to the number of vertices squared for a dense graph. In a fully connected graph, the number of edges will be of the order n square, where n is the number of vertices. And in a sparse graph, where every node is connected to k nearest neighbors, for instance, then the total number of edges will be k times the number of vertices. Now, the algorithmic complexity of the original Dijkstra's algorithm was order v squared, where this denotes cardinality of the set v. So that's OV square is actually O of the number of elements, the cardinality of the set v squared. Now, more recent, it's not so recent, it's actually in the 80s, an improvement to Dijkstra's algorithm was proposed, which used min priority queues, and that gave lower complexity, which was order E, which is the cardinality of the set of edges, plus V log V. Now, in big data applications, the number of vertices is equal to n, which is the same as the number of samples. And we generally use something like k nearest neighbor, in which case the number of edges is equal to kn. Now, the original Dijkstra's algorithm will have, therefore, if this is the original Dijkstra's algorithm, the complexity will be order n square. And since Dijkstra's algorithm gives us the shortest path to all vertices beginning from one given vertex. Now, if I have to find all possible pairs of shortest path from any vertex to any other vertex, then I have to run Dijkstra's algorithm n times. So n times order n squared is order n cubed. So my Dijkstra's algorithm is of order n cubed in order to find the shortest distance from any vertex to any other vertex. End.